Okay, it's about the time. Let's go ahead and get this started. Okay, yeah. Okay, good evening. And let's go ahead and get this started. I think in last chapter that we were talking about just pretty much that two variables. Okay, we were talking about the two variables, how they were related. Okay, in the very beginning we had only one variable. Later on we added another variable, and to explain the second variable with the aid of the first variable. Okay, we had that kind of a discussion. Then we were looking into that different categories. We have mainly two types of data. One is numerical or quantitative. The other one is qualitative or categorical. Okay, based on those classification, we had a very broader discussion in chapter 4 to represent the graphical representation of those explaining the one variable with respect to another variable. We did that one. Okay, so what we're going to do that we're going to little bit go further down and then try to find out some kind of a mathematical or statistical model, not the graphical representation. Now we are trying to do the statistics or the data analytics. In order to do this data analytics or statistics or that mathematical come along with some kind of a mathematical approach, we really need a model. We need some kind of a model. How the model can be built up in that way that we can easily generalize what we were doing. That means like most of the time we have a data. With the aid of that data, we can generalize the whatever that variable, that characteristics of that individual or component that we were talking about, we can generalize to the everyone in that particular population. Excuse me. So here the population, we had a very clear idea about how they differentiate from each other. That population means that the collection of all individual component and or that chemical, electronics, electrical, or any components, or that subjects, individuals, anybody, members, anybody whose characteristics being studied from, since we cannot access pretty much everyone in that particular population, but we're gonna do that. We're gonna go ahead and pick a sample, and then we talk about different sampling techniques, and then we pick a sample, and we're gonna just do some kind of summary statistics. Summary means like instead of that talking about individual data values, let's say that for instance heights, weights, we can just summarize and then talk about their quantiles, percentiles, their averages, medians, modes, those kind of a thing we can talk about. But then we're gonna just a little bit go further down, and in chapter 5, what we are trying to do, we are trying to find the model to explain one variable by another variable. But we're gonna come up with some kind of a model. Model not gonna give you that when you're gonna estimate, you have to do some procedure called the estimation, because that when you are trying to get like a population, some kind of some quantity be evaluated. That means, let's say for instance, that average height of all national university student you cannot access. You are kind of like looking for an estimate. You cannot give that exact value for that one based on a sample. So when you're going to make that kind of estimation for the population, that quantity called the parameter, we call the parameters, because that's the unknown term. You don't know the average height of all national university students. You don't know. You've been entrusted by the administrators and say, hey, give us like an estimate on, give a very good estimate of what's the average height of all national university students. That if you're entrusted with that kind of a task, you're going to pick a sample, you do some kind of pick a certain number, like let's say 100 students, and then we're going to measure their heights and then take the average and then make an inference. But that's kind of like something that we do at the very primary stage. But that's not that very statistical or analytical or mathematical way of doing. Then instead of picking one sample, you're going to pick so many samples and then get the averages, and you're going to find the average of the averages. Some kind of that kind of procedure we're going to utilize. But even with that one, when you're going to go back and make some kind of a conclusion about the population or the average height of all national university students, you're going to make you're not going to give the exact value that they were expecting. Sometimes the value that been already, they know that, let's say the administrators already know the value of average height based on another kind of a survey done by someone else. They have that one in their hand. But that's called the average height for all national university students from another survey. But from our survey, whatever the value coming from our sample, not going to be exactly the same value that we have for the population population parameter or population unknown term. So they're going to differ. That difference is called the error. So there would be some kind of an error incurred when we are trying to estimate the unknown parameter, because we are trying to estimate based on the data. Data means a sample, but we're going to make that estimate to make a conclusion or inferences about the population parameter, which is the average height of all national university students. Okay, so in that such a situation that we should have some kind of a model, or plus that there would be some kind of an error incurred. Okay, that error has to be minimized. Error has to minimize throughout this all the statistical and data analytical process. What we are trying to do, that mainly that we are trying to minimize the error. How to minimize the error? In order to minimize the error, you have to look into a certain model in which that error term has been included, and then play with that one, and then do some kind of a statistical procedures or mathematical procedures and try to minimize that one. But before we're going to get into that one, sometimes that you're going to do some kind of a good estimation. In order to do that, like a best estimation, you have to come up with the best fitting model. The model that your data fit very well into that one. It's some kind of a structure that you can utilize for any given data for that kind of a scenario. That's called the model. Model is some kind of a structure, mathematical structure. So that's the one that we are trying to little bit, not in a deep, that we're going to just go ahead and learn about that one on the surface, and then later on that down the road that we can dig deep and see what's going on. Okay, so I'm going to go ahead and then share the other screen and then see what we have. Okay. Share. Okay. We share some screen, this one. Look at here that they were interested in this kind of a situation. See, they say that you may have that people talk about statistical model. Someone may say that I built a model based on the data. Model has been built up based on that. Our model predicts something, blah, 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 like that. Okay, most people have such statement, just not their heads, okay, knowingly. Okay. See, most people who hear such statement just nod their heads knowingly, but inside they are wondering, what does that mean? What does that mean? What does this mean actually? Even though that they're going to shake their heads and say, hey, it seems like they know about that one. What that really means? We introduced the idea of a model by analogy. Let's say that you want to estimate the area in square miles of the state of California. You want to find the state of California like this. You want to find that area of this particular state, California. But if you want to do that one, it's not easy, because California has a large and irregular shapes. Look, see, it has a very irregular shape. See, it's not easy for you to measure that. Because of that, what they're gonna do, they're gonna come up with some kind of a model that are available. Some models in which that we can easily measure the area. See, they're going to divide this into 3 parts. One, the top part looks like a square. Here, that in the middle part look like a triangular. This one, see, rectangular. See, you're going to use for this part the lower portion, that rectangular shape, the middle portion, you're going to just come up with some kind. These models are already been developed. This is a model. This is a mathematical model. This is a geometrical model. Because when you have irregular shapes, if you cannot find it, you have to jump into a model in which that they have that structure, some kind of a set into that, come up with at least or approximate value for that. That's to tackle that situation. See, approximately you can see find some kind of area. But this is for that. See, the formal shape. These are, see, these not formal shapes. But if you have a non-formal shape, in most of the time we don't have a formal shapes. What we're gonna do instead of that, you going for all these that pretty much area, roughly, approximately, or you're gonna come up with some value called the estimate. See, you're gonna fit in the upper portion with this model, this part with this model, the triangular model, rectangular model. See, one thing that notice about our model at the outset is that it's not very good. See, most model, in fact, are pretty bad. Although the model is vaguely California-like, there are a lot of details that are not captured in the model. See, but it is better than nothing. Even though that they were thinking about this not going to be the perfect model, if you have something to at least to get an idea or the estimate, rough idea, that would be more than having nothing. See, let's say that in a certain situation, some people come up with and fit in this one, see, pretty much in such a way that almost, see, cover everything. This one, somebody going to come up with a smaller one. See, that most of the area not being covered. See here in the third model, that most area been excessively covered. See, because of this situation, see, this is called, see, best estimate. See this one overestimate. See, underestimate. See this one. See, it's not a very well estimated. These two are, see, not good estimate. This is, see, excessively estimated. Sometimes that the area, see, there's so much error. See, is so much being excessively that covered that not supposed to be covered. See, here, most of the part being missing. That's another error. See, so this is something that gonna, see, pretty much cover pretty much whole thing, but still there's an error. See, that's why we are trying to minimize the error. See, as I said earlier, you are trying to minimize the error in such a way that you're gonna come up with the best model. You have to pick the best model. Okay. So the picking the best model is another big task ahead of us too. See, notice that in panel C, our model seems like it will overestimate the area of California. See, if you see, take analogy a little further. One, we had decided to model the area of California, two rectangles and triangles. See, two rectangles means this is look like a square, but it's they're gonna call the rectangle too. That doesn't matter. We try to make the model fit as well as possible. To do this one, we adjust the size and placement of the geometric shapes. Here are a few examples. See, in 3 ways. You can see that our model seems like it will overestimate the area of California because we made the shapes too big. In panel B, the model looks like it will result in an underestimate. See, it's not enough for you to that cover the pretty much the whole area. The model in panel A, however, looks pretty good. We might say that the model in panel A is the best fitting model. So see. So note that our judgment of fit comes from looking at both the area within the state that is not covered by our model. See, the yellow parts sticking out in panel B, and the area not in the state that is covered by the model. See, the blue parts of that are not overlapping with the Californian panel C. It is useful to think these two areas as deviation from the model or error. See, as I mentioned over here, if you see, it's still that they have some kind of error. Error means like that this total area not being covered with our model, but still okay that this is that maximum that they can do. See, here, see the way that they estimate that this model not gonna cover that much. This one, see, underestimate, overestimate, and these are not being covered or excessively covered areas are called the error. See, therefore we're gonna write area of California is same as equals to area of the geometric figure plus other stuff. Other stuff means like a error term, error incurred by estimating the area of the Californian state. See? Error incurred. See? That error has to be minimized. This is here minimized. See? So see, the other stuff would be the deviation. These are called the deviation or the error, both positive and negative from the model. It is useful to think of the best fitting model. See, best fitting model as the one that minimizes the deviation. See, best model would be the one that minimizes the deviation or the error, making the other stuff as small as possible. See, you are trying to, but that's the problem in that all the physical phenomena that we explain through the mathematics gonna go up to here. They think mathematicians, they think up to here only. They think area of California equals to area of a geometry. Everything, anything that we're gonna see in that all kind of a phenomena. But there's an error when you are doing some kind of estimate. That error part has not been included when you're gonna learn something. But some people do some kind of a mathematical model. They did not include the other stuff. That's why it's called mathematics. When it's come to the statistics or data analytics, they have included, mainly the statistics, they have included this part. When it's come to the data analytics, what they are trying to do, they are trying to minimize this part. See, it goes like that, okay? So area of California equals to area of the geometric plus the error incurred. See, this is the model, see? See, this is the model, see? It is also important to note that the geometric model of California is a gross oversimplification of all the different attributes of California one might be interested in. Models are always like this. They oversimplify some aspect of the world, see, and focus in one, only that dimension you are most interested in. So that's, see, so that you can think about that, come up with some other models too. There's not any fixed model, okay? There are so many other models that kind of fit in into this one, this scenario, but the thing is make sure that it's gonna minimize the best model gonna minimize the error term. See, modeling a distribution with a single number. Rather than talking about the distribution, you can remember the distribution. Distribution is the variation of the variable. The graphical representation of the distribution is, one of the graphical representation of the distribution is the histogram. How could you gonna show that distribution graphically? So that's a histogram. The other one, histogram has several ways of, we did that one last time, okay? We did the histogram for just one variable, and then with the two variables also. Two variables means mainly histograms are for the quantitative variables. Histogram cannot be drawn for categorical variables. You know that one. It's a fact. Histograms are for only quantitative variables. And later on, quantitative variable as a one single one, we did that one, having that one on x-axis. Later on, same thing we did by having that one on x-axis, but it's been explained by another categorical variable. Can you remember, let's say the thumb length being explained. Thumb length is quantitative. You can easily draw the histogram for that. You have a code. You can use the R codes or R programming for in order to get that value. You don't have to do anything by hand. But later on, we just kind of like did the more analysis based on that gender, male and female. Then we drew that histogram vertically, that faceted histograms, vertically, horizontally. Later on, that we were interested in knowing that not the histogram, just the dots only, called the dot plots for the male and female of the thumb length. Then we were not interested in the dots. We were interested in the scattered plot for female and male of the thumb length. We did that one. We did another one called the box plot. Then we put the box plot and this scatter plot together, called the jitter plots. Okay, scatter plots mean the jitter plots in that case, that put together, and then we drew that almost like a 7 type of that histograms. Sorry, the graphs for quantitative variable. Just for the quantitative variable by itself, we can just draw that histogram only. But when with respect to another, or that when explained through another variable, which is categorical variable, We drew that six types of seven types of mainly seven types of graphs. You can remember. There we were talking about the distribution. Then the distribution has a graphical representation. Now what they're gonna do, instead of talking about this whole distribution, they were interested in one point. See, that's why they say that a single number. They say that why we're gonna just talk about this whole distribution? Why we cannot focus on one point? What is the most important point in this kind of a distribution? If it is right skewed, left skewed, can you remember we were talking about by looking at this and see it seems like a right skewed. If you want, you can think like see, look like a bell shape. See, symmetry. For any kind of a shape that we were talking about the single numbers. There are major three single numbers: mean, median, mode. We discussed those ones at a certain point. Okay, we can talk about that one again and again and again. But they say rather than talking about this histogram, see the age of housekeepers. It's coming from this age, housekeepers' age. And on the other hand, you can remember we drew two types of histogram, mainly two types, one for the population, one for the sample, okay? One for the population, one for the sample. As here that for the based on the given sample, you do the histogram. If you want to just do this one for the whole population, you can remember these are systematically come to what? Become like a uniform most of the time. Most of the time, if you do that one, they are coming from uniform distribution because the larger the number of that size of the sample, instead of using like, let's say that here, if you're using like 157 housekeepers or 75 housekeepers, if you increase that one to 1,000 housekeepers, you pretty much can have a distribution very flat distribution. You know, that's getting very close to the population. So that's why most of the distribution, they believe the shapes are coming from uniform distribution. Uniform distribution is the basis. So this one, so that's what they were trying to do. Instead of now going through this whole distribution, in this graphical representation of the distribution, see, that's the graphical representation of the particular distribution. My distribution variable, I'm going to draw the variation of my variable. Variation of the variable has been manifested graphically, see, graphically. Then we took a smooth curve, we scheme a smooth curve, scheming we draw a smooth curve scheming the top of this histogram, and then take that out, and then we figure out where the mode would be, where the median, where the mean would be, those places. In addition to that one, if you want, you can easily locate Q1, Q2, Q3, minimum, maximum, those things, even on that distribution. That's the same thing we were talking about in 5-number summary. And the box plot, that's another variation of histogram. That's a kind of a histogram in another form. We talk about, see, somewhere here, see, minimum, maximum somewhere here. Somewhere in the middle, we have a mode with the highest peak. Highest peak is the mode. And then very close to that one, median, which divides this into two parts, 50%, 50%. And the total area under the curve will be 100%. The area is nothing but the probability. If you're going to talk about the probability, that's a chance. It's the same thing. And then the mean is at the center of these numbers. See? So that's why in this graphical representation, instead of going and then talking about that, all these, they were trying to just stick to one number, see, single number. See, that's I say, building on the concept of model. Let's now develop what we mean by statistical model. Whereas in the previous section, we are building a model to help estimate the area of the state of California. We now want to build a model we can use to characterize the distribution. Exactly. In order to characterize this one, this can be characterized by the model. As you will see in the subsequent chapters, statistical models are very useful. We use them to summarize distribution. See, it's a summarized distribution. We use them to make prediction about what the next observation added to sample distribution might be. See? And we use them to explain variation in one variable with another. But we still start with the simplest model, which we use a single number to characterize the distribution. See, That's why we really need a single number to characterize the distribution. The whole distribution, you're going to summarize, condense by a one number, single number, because most of the time we use the mean or median or mode. But in this discussion, we are mainly focused on mean. See, at its most basic level, statistical model can be thought of as a function that produces a predicted scores for each observation in a distribution. By function, we don't mean an R function. We mean a mathematical procedure for generating number based on the data. That means here function means not the R function. R function means like once you get the shape of this one, you can write the mathematical equation. That's called the function, equation for that shapes. That's the heavy stuff that done by the statistician. They do that one. That was something we don't need at this stage. But when you're going to improve that your knowledge, even that shape, mathematical one going to be sometimes you don't need it. When you're going to fit into the data into that one, it's already programmed with that particular equation. Okay, that's why they say that function here doesn't mean the R function. It's not the R function. They were talking about that the shape of this particular distribution can be explained by a mathematical equation. That's what they say. Okay? But that's why we simply go for the simple model and then try to explain the whole thing. If you see, if you had to pick a one number to represent the entire distribution, how would you pick, and what would it be? See, thought of in a different way. If you wanted to predict what the value of the next randomly chosen observation would be, what would be the best prediction? In order to make some predictions, okay, what would be the best number, single number that would represent the whole thing or characterize the whole of distribution? Let's look at some distribution. What single number would you choose to represent the model of this distribution? Age housekeepers. Why? If you wanted to predict what the next randomly chosen observation would be, what would be your prediction? What single number would you represent or model this distribution? Weight of housekeepers. Why? If you wanted to predict what the next randomly chosen observation would be. Because when there's a number, if you know that some kind of now one single number, rather than looking at this distribution, looking at this graphical distribution, you cannot predict, you cannot talk about nothing. Beyond that one, only thing that you stand still. You cannot do nothing. You had a data. You know that you have a quantitative variable called age or weight. You drew the histogram. Okay. Now you're happy, you have the bars and everything, you can change that number of beans and you can play with that one. You can change the color, you can change that outline. That's it. That's not what we're expecting you to do. You have to make a prediction. Prediction means with the aid of this model, this is a model, you can predict what's going to happen. Let's say that they're going to add another housekeeper without measuring anything, by looking at the shape of this distribution. With the aid of that single number, you can predict and say the next housekeeper's age would be this much. Next housekeeper's weight would be this much. They can predict that one ahead of time. It's important. It's very important in this the corporate world and in this the business world. It's going to be very, very useful for that. The future plans and the predictions going to be very useful. They cannot go individually and looking at something and make the prediction. That's why they need a model. This is the kind of a model. The model will be characterized this distribution. Distribution is coming from data, but the data you have the data, you have a histogram or whatever the graph you have, not enough. You have to make the prediction. In order to make a prediction, you have to come up with that different model. That's the model that we have. Different model means not the model that fitting into this one. Another model that one to explain one variable over another variable. The way that we did earlier, we say that the area of the California equals to the area of those geometrical figures plus other stuff like that. See, this is also a model. This can be given by an equation as well. That's what the mathematician has done. But by looking at this one, in order to make a prediction, what would be the best number you can talk about the average. If you know the average of this one, on average you can say, hey, for this kind of a shape, if you know the average, on average you can say, hey, the next housekeeper who's going to be added to this going to be at this, on average, he's going to be at this age. He's going to have this kind of weight, or those kind of a thing you can predict. That's why now they are looking for some kind of a number to make the prediction. See, what would be the single number would you choose to represent the model that distributes the predicted GPA students? See? Why? If you wanted to predict what's the next randomly chosen observation means randomly chosen student, okay, would have what would be that next student, that randomly pick next student GPA would be, what would be your prediction? See, this is looks like a left skewed. Excuse me, see, left skewed predicted GPA. This is more like a bell shape. This is more like a right skewed. You can remember those three shapes mainly. In addition to that one, mainly there's like a flat line called the uniform. Okay. See, now see, this is a bar graph. See, what is the best value to represent or model the distribution of race, ethnicity student? Why? If you wanted to predict what the next randomly chosen, but in this, those are up to this point, GPA, weight, height, sorry, age. Those three are quantitative variables. That's why we have drawn the histogram. See, histogram. See, these histogram are for quantitative variable. Mostly that quantitative variable, the best value would be the mean. But when it's come to the categorical data, like this, race, ethnicity, the job status, like the bar graph, these are bar graph. Look at the bar graph. If you want, only thing that you can see, they were not attached to each other. See, they were bra. See, this those are bar graphs. See, this is a gap. See, there's a gap. So this one, if you want to predict something for the next one, see, they say that if you wanted to predict what the next randomly chosen observation, randomly chosen that, let's say that a student, what would that student race or ethnicity would be? That it is completely based on what? The mode. Mode is the highest peak. The most frequent one, see? Most frequent one. See? Here, look at the most frequent one, not working. If you pick another person based on this model, he should definitely on average, most of the time, you can say they are not working because the highest peak would be this one, see? That's the mode. See, mode will be utilized. Mode is utilized for categorical data, okay? So look at that. In addition to that, you are thinking about a single number. Then depending on how the variable is measured, quantitative or categorical, and the shape of the distribution, we will use the different procedures or different function to choose one number as a model. As I said, based on whether quantitative, you're going to pick the set single number mean. If it is categorical, you're going to pick the number, the single number mode. You're going to summarize everything by the mode. You don't have to worry about the shape or anything like that. Shape is important too, because in that way that you can figure out what the best thing to be utilized. See, in mainly, if I write over here very clearly, related to this one, I'm going to open this one. I'm going to bring this here and write something. I would say this one. Why these three, mainly the three quantities, we were talking about three quantities, okay? So out of these three, that single number related to this particular distribution is the variation of the variable. We can figure out what quantity or what single number gonna go with what type of data or what kind of a shape too. Not only data type, we need to focus even on the shape as well. Okay, this is what I was talking about. Then for the quantitative data, data, you mainly draw the histogram. See, you have a histogram. So categorical data, you mainly have a bar graph. See, bar graph. Now, for these shapes, see, you saw the different shapes. See, I'm gonna draw that smooth curve only. This is, I'm talking about this. See, histogram is already there. See, histogram is already there. You get the smooth curve to get the shape, or you can sometimes see right skewed. See, and on the other hand, see, left skewed. See, See, left skewed, or sometimes see, pretty much the same, uniform. You can remember. So they were. If you come to this one, you can remember that you have the mean, median, and the mode gonna all at the same place. See? So you can use mean for this kind of a scenario. Mean gonna be at the center. Here is the highest peak. This one, I'm talking about this one. That's the mode. But we're not going to utilize the mode in the right skewed still, because we were talking about this quantitative data. I'm going to use this median. Next one, I'm going to use this guy. See, mean. That's the single number. That's the single number I'm talking about. Here, this is the single number I'm talking about. Again, the mean. See, mean. See. But if you have that, I'm going to little bit change this one rather than this one. See, rather than this single number, I'm going to make a little bit change this one to make it more precise. Even the categorical, since this is skewed, I would like to use single number as a median. Median would be my single number this time. Not the mean. Mean can be utilized when it's symmetry. Again, here, quantitative variable, these are quantitative, okay? So the highest peak would be the mode. Then right before that one, you have the median. And right before you have a mean. Since again this one, this is the single number I'm talking about. See? That's the median, this time median. See? If it is this one, you can easily use what? The mean and median going to go to the same place. You can use the mean. That's my single number. Everything can be summarized by the mean if you have a uniform shape. This is a left skewed shape. This one is a left skewed. This one right skewed. This one symmetric. We can remember that we did this one symmetric. This is the right skewed. This one left skewed. This one uniform. You got the shape, but you can use the mean. But on the other hand, see, on the other hand, this is for this first one for quantitative data. Quantitative data or variable doesn't matter. Histogram, I'm talking about histogram. You draw the histogram and get the smooth curve. And the second one, you have a categorical data. See, categorical data or variable doesn't matter. Then you're going to draw the bar graph. When you draw the bar graph for that one, you have a bar. See, like this. Here we can go ahead and we're not going to go ahead and look for the average. We're going to look for the what? This is frequency. See, this is where the variable or data, the same thing. Okay, then you're going to go ahead and see the thing, highest frequency, which is called the mode. That's the single number I'm talking about in categorical data. See? If you have a categorical data, the single number you have to utilize is the mode. You can make a prediction based on the mode. See, based on the mode. If you have like a skewed categorical but skewed median. If it is symmetric, you use the mean. That's what I want to emphasize over here. See, so our discussion assumed that we are doing a very heavy assumption here for that for the upcoming discussion. We're gonna believe our all data. It's very hypothetical. Data gonna fit into the bell shape or symmetric distribution. That means that you are using mean. Because you might be thinking that when you get a data set in a practical application, in a world, the real world data not going to fit into symmetric, because we use the symmetry for the mathematical tractability and easiness to build up the model and then play with that one at this primary stage. Otherwise, if you go ahead and play with the median, thinking that, oh, my real data, if I fit in into this one, I saw a histogram like this. Now what I'm going to do? Can I use the mean? But they still use the mean even for this one. But mainly what I'm saying, they were assuming that even though it looks like a right skewed, left skewed, J shape, there are more other shapes too that keep going up, going down. See? Those shapes we haven't talked about that, but here, let's see, sometimes that, see, going down only, see, like that, see, like, see, they're not gonna, they start from the top and go all the way down and hit on the x-axis. Or sometimes, see, from the starting from x-axis, go down, and then those are called the J shapes, see, this is a J, see, this one reverse J. Reverse J like that, we're gonna have a different shape. But any of these, even you get this shape or this shape or this shape or this one, in the quantitative variable, regardless of the shape, they're gonna assume it's gonna be bell shape. In that way, they're gonna use the single number as a mean. They play with the mean. So when you give that heights, thumb length, they're gonna go to the average thumb length and try to looking into that other stuff. So if they want to looking into the thumb length with respect to that gender, that's or with respect to the weight, then that discussion or model come along with some kind of a heavy assumption that that distribution for thumb length is definitely symmetric. Okay, that's what they're trying to do. But mainly, we're not going to talk about that categorical data at this stage. In that way, you don't have to worry about this one. Categorical data, mainly we focus on that for the y-axis, what you're going to go to the y-axis. So all the time we draw the histogram for the quantitative variable, but that quantitative variable can be explained through another quantitative or another categorical. That's a different discussion. Okay, that's why they were kind of they were giving that heads up earlier. See, look at here how this error can occur. So the same thing that I'm talking about is they are focusing mainly on the symmetry. See, they were here. Even with that one, there are errors. See, depending how a variable is measured, that we talk about that one. Measure means like the categorical or this one shape, the distribution. We use the different procedure means like a different function. Function means mean, no, median, no, mode. For a quantitative variable whose distribution roughly symmetric and bell shape. See, a number right in the middle might be the best fitting model. Number in the middle would be the best fitting model. You know that most of the data clustered at the center. In that way, they think mean would be the best one. In a bell shape, this is a symmetric and bell shape. Okay. See, and if a distribution is skewed, life of the best model might be number of two, where the middle would be. You ignore the long tail on one side or the other. For a categorical wave, the best model general category is the most frequent, as I said. See, categorical mode, most frequent one. If a distribution skewed left or right, the best model might be the number toward where the middle would be if you ignore the long tail on one side or the other. So what they were talking about, as I said, that again, they say that, you know, that what they were talking about, exactly what I talk about. Regardless of this, even this right skew, they say, doesn't matter. We're going to assume this one as like a bell shape and then play with that one. How do they going to assume that one? They're going to cut this tail part. They're going to take the tail part out, thinking that it's not going to affect this one. But it's not the proper way of doing that. If you once you cut that one, it's become truncated data. Then you have to play with the truncated data different way. It's not going to fit into that model very well. But they assume even though you cut and it's not going to be harmful, that harm can be that they explain in the higher level, but they say, okay, we're gonna ignore this tail part on this side or that side, and then make it like a symmetric. See, then it's like most of that data being clustered around not the median, then the mean. They say still mean, we're gonna take the mean. J shape doesn't matter. Cut that all that unnecessary part and take a L shape or something like that, symmetric shapes. Okay. That's what they were telling over here, the same thing that I was talking about. See, categorical. Let's zero. See, let's zero in non-just distribution of quantitative variable. Take a look at these two distributions below for variables 1 and 2. See, what number would you choose as the best model for distribution in navy blue? See, this one, middle for sure. No? What number would you choose as the best model for the distribution? Oh, sorry, this one. I'm sorry, it's a navy blue. I'm looking at the wrong one. Yeah, see, still the same. See, but look at that. Look at what happened. Here is a high peakedness. High peakedness. It's been flattened, but it still have the same number at the center will be taken into account. See, it's been distributed on both sides. See, more variation, something less variation, but still that single number would be there. In which case the model a better fit for the this one. See, a single number, even a well-chosen number, it's not a very good model. It may be a better model. See, in which case the model a better fit for the data. Better fit for the data would be this one, that most of the data been clustered around the center rather than it's been spread out on either side. See, so out of these two, see, this would be a best model. See, that's why we say the data, that's the model. Can you remember? Plus the error. See, this is the way how we're gonna write the data. Data means that what you're looking for. See, your data not exactly fitting into model. There would be an error. So you saw that this model area of the geometric figures not gonna very well fit into that one. But at least there was a one good model that pretty much cover everything, minimizing this error. See, there's an error part. See? So that's the way how you're gonna write the model. See, that's how we, as I said earlier, the mean taken as the model. See, mean taken as the model. Median and mean, two possible functions for generating model prediction. As I mentioned earlier, that out of mean and median, they're gonna pick this one. Look at that. For a quantitative variable, statistician typically choose one of the two numbers, the median or the mean. The median is just the middle number of the distribution. Take the following distribution of 5 numbers. The median is 5. See, you're going to arrange this one in ascending order. See, 1, 2, 3. From coming from this side, 1, 2, 3. The 5 would be your median. That is just sort all numbers in order. See, then the number in the middle is 5. You can see that the median is not affected by outliers. So if you change the 20 in the distribution to 20,000, the median would still be 5. See, even if you're going to add more numbers. See, even if you change the 20, see, change the 20 in the distribution to 20,000, see, doesn't matter the value. The median means just the location of the data, not the value of the data. Even if you change this one 20,000, still 5. But to calculate the mean of the distribution, we simply add all the numbers in the sample and divided by the numbers. So the mean of the distribution is 9. Both mean and median are indication of where the middle of the distribution is, but they define middle in different ways. Yes, here means that that's the mean means that, see, mean means center or the middle of the data values. Median means center or the middle of the location of the data value, location. That's why that extreme value that in that particular data set, even if you change that 20 to 20,000, it won't affect to the median. Median not being affected by the extreme values. That's the very reason IRS, that when they calculate that income, they never gonna talk about average income. They always talk about the median income. If they calculate the average income, this will be distorted, because then that that value being affected by the extremely wealthy people's income, gonna affect to that one. Because of that reason, they talk about the median income. In that way, you can go ahead and look into the the middle location or middle value. Okay, see, you're not gonna set the middle location and then read the value at that location. You go to the middle location, which is third location from the top, and another third location from the bottom, which is 5. If you have two numbers coming from the both sides, like when you have even number, then you're going to add the two numbers together and divide by 2 and get the average of that one. Anyhow, that the median will see 20,000. That's why that you want to know that where that your income would be that explained through the median, not by average. Average, if you put that one, it will be shifted heavily. See, to calculate the mean of the distribution lambda, the different way. Phi and number, sorry, see, to calculate the mean of distribution, we simply add all the numbers in the sample and then divided by the sample size, which is 5. So the mean of the distribution is 9. Both mean and median are indication of whether the middle of the distribution in different ways they've been explained. Phi and 9 represent very different points in this distribution. See, phi is the middle location. 9 would be the middle value. Middle value. See, if in R these other these and other statistics are very easy to find with the function favorite statistics. See, this is the function you can remember. Create a variable called outcome and put in these numbers to 5, 5, 5, 10. Then put the variable into a data frame called tiny data. Finally, run the favorite statistics function on the variable outcome. Let's say that we have a numbers. See, these 5 numbers, 5, 5, 5. See, this data set, small data set, tiny data set. See, 5, 5, 5, 10, 20. And then put the data into, see, tiny data into a data frame. See, you can see the outcome. Now the data, put into a data, see, that's the variable. This is the variable. Variable has a numbers. Like a height. Height is variable. That variable has numbers. Individuals' values. See, same way, this is the variable. This is the variable. This is the data. See, that's the variable we are interested in. We're going to run favorite statistics for the variable for that particular, coming from that particular data. You see, you can easily find the minimum. Minimum is already, we know. Quartile 1, median, Q3, quartile 3. And the median is the quartile 2, maximum, mean value, see, standard deviation, n number of, see here, I'm sorry, this is 9 mean, the standard deviation, we're going to talk about that one later. N means number of data points, there are no missing values. See, if you want, you can save this one to favorite statistic into R object. See, that's how they were going to do. They're going to save this into this one called the outcome stats. When you save the result of favorite stat, you would end up with the data frame where the columns are the different summary statistics. If you just wanted to output the mean of the outcome stats, you could write outcome stat mean. I think the mean is a variable in the data. But that means if you really want to read the mean of this data, the way that this has been set up, see, you can easily go ahead and calculate mean. Or they say, go inside that, give a name for this favorite stats. And that one they're going to consider as like a data set. See, 5, 5, 5, 10, 20, 9. This one's favorite, like a data set. Within that data, you can go to that variable. It's going to consider these as like a variable. If you go to that, the name where this has been saved, and read the mean inside that one, see, mean inside, see, that would give you the mean, see, that's how it says. You go to the outcome.state. If you need the median, you do the same thing, see. If you want to read this one, see, this is what they were talking about. They say that get this one and then save this one to favorites, five number summary or these favorite statistics into something called, see, outcome stats. See, those are the statistics of the outcome variable. See? Outcome variable statistics are this one. If I run, I don't see this one yet. This is for that one, okay, not for this one. Now I'm gonna go ahead and say, hey, go to this outcome dot stats, and inside that one, I need the mean. Give me the mean. Okay. See, that's gonna give you the mean. See, single value. If you change this one to, let's say that median, median, you can see median. Median. As a mean. So in like that way, can we calculate the mean in this way? Mean, whose mean? See, this guy mean. See, outcome. See, outcome data. See, look at this one. See, mean of outcome. See, you can straight go over there and then read that one to another way to calculate mean. See, the other way to calculate, go to this variable and say, I need the mean of this guy. Can we calculate the median the same way? Median of outcome. I'm sorry, median. See, either this way or this way. See, you go to the favorite statistics and then go inside and read it. Okay, there are benefits of that one too. If you want to do this one, if you're looking for the standard deviation, you can go do it this way. See, look at the standard deviation. You go inside this guy, outcome stats, where that you have saved the favorite statistics of that data set. Okay, SD. If you go inside and ask for SD, it will give you SD. See here, see 956. I'm talking about these three. See 6.1. The same thing. Can I get it from a different way? SD, go and then go straight to the variable. You don't need to do any fancy thing like that. See? Still you get the answer. Either these three ways, see, or this way. See, like that. See? Then if you want to see that size of that one, see, you can easily go and say the size would be this one. Q1, quartile 1. If you want a quartile 1, let's say that you go to this one and then if you put Q1, would that give you what you're looking for? See? So I'm talking about this. Okay, not the last set, not these three. 1, 2, 3. This Q1 can you remember 5? See, that's 5. Okay, this is I'm talking about this one, not these three. If you're gonna go from down, see 1, 2, 3. This one I'm talking about this guy. This guy for Q1. See, you can ask for Q1. See, if you want max mean like that, rather than that, can I get the Q1 from here? If you do like Q1 here and then go to outcome, would that give you that one? Let's see. Oh, they don't do like that one. Only for, see, only for that standard deviation like that. If that's the case, you have to that sometime for the Q1, you can just see, go to favorite statistics and get that one. See. So on the other hand, you go to this one that you're gonna count. Look at another way of doing that one. Let's say you need the mean. Okay, you say that you have a favorite stats. Okay, outcome stat. Okay, copy outcome stat, and you're gonna talk about its your mean would be what entry? 1, 2, 3, 4, 5, 6th entry. If you put like that, would that work? Yes. Still give, see, even this time we're gonna give even the mean name. See, whole thing. See, 6th entry. Another way to looking for the mean. If you want go to outcome stat and rather than go to that mean, you're gonna say give me the 6th entry. And if you want median, see, outcome stat that data means like the 5 number summary. See, median would be in the 1, 2, 3, third entry. I'm gonna get the third entry. See, it's the median. And if you need the standard deviation, pretty much go to the same thing and then say my entry, the name of the entry within the brackets. That entry would be standard deviation on the 1, 2, 3, 4, 5, 6, 7th entry. See? Very clearly that you get pretty much everything. See, so many ways to get this done. Okay, see, there are 3 ways that I was showing over here. You can go straight to the variable, or you can go to the where you have saved and then called by their names or called by their location. See, 6 location. Please read me the whatever you have at the 6 location. But if you want to mean you have to figure out where the mean must be. If it has 6 location for your calculation, sometime if you want, you can do like this way, or look like this way. See, excuse me. Let's say that you want to multiply the minimum and maximum, or take the difference between min and max. If you want to write the program like not for only for this one, for that any number, you can simply go to write with the min and see. Let's say that you can get the mean from this one. See, mean for sure for this one. See, so if you go to the mean of outcome, you get it. Yes, it should come. See, it should be somewhere. That's why we don't. Minimum is 5. See, is that 5 minimum? Yeah. See, right there. So many ways we can do that, and that's why I say if you want the median, you can go like this way, or there are so many other ways of doing that one. See. Now see, if you are trying to choose the one number that would best predict what the next random sample value might be, the median might be better than the mean for this distribution. With only 5 numbers, the fact that 3 of them are 5 leads us to believe that the next one might be 5 as well. See, if you are trying to choose the one number that best predict what the next random sample value might be, okay, the median might be will be better than the mean for this distribution. With only 5 numbers, the fact that 3 of them are 5 leads us to believe the next one might be 5 as well. See, that's what they were saying. Either you can look into the mode or median, because it's skewed for sure. How could you know this is skewed? By looking at this one, this data set skewed. See, 5, 5, 5, 5. 5 has occurred 3 times, 10 has occurred 1 time, 20, see, far away, see, maximum value, far away. So your mean, median, see, mean, median, see, right skewed or left skewed. Now we have that if you put the data, right, put in at this data, see, you have a 5, 5, 5, 5, 5, 10, and 20. See, for that particular data set. See, if you put to this one, see, look at the 5 has occurred 3 times. See, 5, then 10, 10, 20. See, this one 1, this one 3, this 1 time. See, look at that. If you draw like a thing, something like that, it's gonna be like this. See, your median. See, this is the mode, highest peak. Then your median should be somewhere very close to that one. You saw the median. Median would be 5, 2 in this case. See? It came to that one, very close to that one, 5 as a median. The mode also that one. Mean, it will be 9. See, 9 mean. It's the mean. It's the median. If median is much closer to the minimum than is to that maximum, it's right skewed. See, it's median. Looking at the median, see, skewed. If it is skewed, as I mentioned earlier, for this kind of a data set, median would be the best best one to be considered, best single number than mean. Can you remember? That's what they were talking about here. That's what they were telling here. That's why they say that for this particular data set, see, for this particular data set, see, with only 5 numbers, the fact that 3 of them are 5, no, I'm sorry, they say median might be well better than the mean of this distribution because it's right skewed. On the other hand, since 5 has occurred 3 times with the highest frequent, the mode, by looking at this one, the highest frequent one even can consider as like that's the mode. Even though it's a category quantitative data, since it's a small data set, you can think about this one like, okay, see, there are not too many histogram bars. So just only 3 places, 5, 10, 20 only. Because of that, you can think about the mode can even that consider as like a best the number to utilize in order to make the prediction, and then see, okay, if somebody going to be added to this number, other number, what would be the next number would be. Most probably next number would be 5. Or sometimes 5 and 5, not the mean. See, mean is a little bit far because this kind of the median would be the best one to explain the skewed data, plus 5 also become that they both fall at the same place. So in that way, even more though that the median can be utilized. Other than mean. That's what they were telling over here to get a clear idea. See. So now they were saying that, okay, see, on the other hand, we know nothing about the data generating process for these numbers. We don't know where these numbers are coming. The fact that because the data generating process means about the population, about not the sample, whole population, how it looks like. Its histogram, how it looks like, we don't know. The fact that there are only 5 of them indicates that distribution is probably not a good representation of the underlying population distribution. The population could be normal or uniform, in which case the mean would be better model than the median. The point is we just don't know. That's why they say that we don't know that when we have this looks like this one for the sample doesn't mean when you consider that all the numbers and then draw a histogram, it doesn't look like that right skewed. It may be skewed, it may be symmetry. We don't know. This is for a sample. Let's say that you have a large number of numbers that to represent the population, like 1 million of numbers. If you do the histogram, as I mentioned, there's a high tendency that it's going to get into maybe bell shape or uniform. See, that's why they say. For each of these variables, make histogram and get the favorite states. Okay. For each distribution, what do you think is a better one? The better one number model, the median or the mean. See, model, if this code to make a histogram of the grade predict. See, we can see this one grade predict. See, grade predict. Where the sorry, here see, this is the distribution disqualified. We come up with the recent favorite statistic. And to choose the number that would predict what the next random sample number would be. So histogram. See. So here, see, and then find the favorite statistics. See, favorite stats for that particular this one. See, can I remember? See, it's easy. I'm gonna copy and paste this one, and my variable would be what? Grade predict. See. Data fingers, it's coming from fingers data, and then you can recall that on grade predict stats. See, that's the histogram. Grade predict state, not fingers. Okay. This is the minimum through the maximum through Q1 median, blah blah like that. It's graphical representation on here. See, look at almost like a left skewed. If it's left skewed, you know the reason. Left skewed, your median is very close to Earth. See, close to maximum. See, max value. See, max and median close. Median is closer to, much closer to the max than is to minimum. See, that's why it's left skewed. See, you saw even that one. See. Then see, for each distribution, what do you think that the better number would be? For here, if you go ahead and look at what would be the better number, mean would be 3 point something. See, this one, median is 3.7. What do you think? They're both close. Mean and median both close in this case. Either one is okay, 3.7. For this one, right skewed you can use because if you are using with the small data, but if it's a large sample, so some models, you still use the mean. Okay, the same way that we can do the same thing for another variable. See, thumb variable. Let's look for the thumb variable and see too. It's thumb variable histogram plus favorite statistics. Let's say favorite stat of thumb. The data would be fingers. Okay, then favorite stat given by, we're gonna print it. The thumb length. Takes a while for them to settle down. Okay. Look at the histogram. Look at here. It's getting, see, in this one, more symmetric. We don't have any doubts about that one. We can see, mainly go to the mean. Look at the median, mean. They're both the same. See, median and mode the same. See, symmetry. Here, median and mean look the same, but we saw that, see, little bit, see, some data over here to spread. See, that's why the shape and favorite statistics both should be taken into account. Okay, look at why number wise 3.7 and 3.6. See, they're close to each other. But when you go ahead and look at the histogram tells a different thing. It says that they were close doesn't mean they were symmetric. No. There are other factors going to affect to that one too because of how that data being spread out. See, look at left skewed. But mean and median the same. In that both cases okay, but most of the time if it's skewed, we're going to take the median. Here, look at the mean and median looks the same. But if you go to the plot, it's symmetric, it's different. Okay, let's see this. Modify the code to make a histogram of age. Now let's do this one for the age. And at the same time, we're going to run the favorite statistics and see that how we can make a conclusion about which single number will be utilized for this one. See, age. Time I get the age, tilde. You know why tilde? You put the tilde because everything going to go to the x-axis in the fingers. And now you can this one, and then I'm gonna see, kept getting, look at how it looks like. See, look at the age. You saw that one. We had an issue. See, 2 humps. 2 humps. Can you remember some data we cut off earlier that some ages were taken out, some ages are missing? Yeah, see, these are 2 humps. 2 modes, bimodal. This is single mode. It's on right skew, the other one, see? But on the other hand, if you go ahead and look at that, this one, see, non-finite value, because see, remove one rows containing the non-finite value, see, because that you have, see, you don't have to worry about that one. See, this one median, look at the mean and median, they're close to each other. But if you go ahead and look at this distribution, see, look at the 2 humps. See, that's why your distribution, shape of the distribution and favorite statistics both should be examined. See, this one, predicted GPA student. See, this one. See, again. See, left skewed, bell shape, age looks like a, see, 2 peaks. Some ages were taken, if not taken out. See, as we mentioned over there. See. That's why they say, see, coming from here, see, grade predicted looks like this, thumb length looks like that, this one looks like this one, see, better number model, see, this is, see, in general, median may be a more meaningful summary of a distribution of a data than the mean when the distribution is skewed. We mentioned about that one, okay, one way or the other. In essence, the discounts the importance of the tail of the distribution, focusing more on the part of the distribution where most people score. The mean is a good summary when the distribution is symmetric. We mentioned that one. But if our goal is to create a statistical model of population distribution, almost always, especially in this course, we'll use the mean. This is the key. I mentioned that we use the mean even if your data is right skewed or left skewed or uniform or bimodal or any shape, we're going to consider them as like a symmetric for mathematical tractability and easiness. Discuss. Doesn't matter like this. As I mentioned, median would be my single number. Median would see here, mean would be my single number. Here, my median would be my single number. See. But doesn't matter, everything will be considered as like a bell shape, and we're going to consider mean would be the best single number to predict the other one. See? That's what we are doing. Because of that reason, what we are trying to do is we are trying to add the mean to our model. That's why we are trying to draw a line now. See, you already know that R code to make a histogram. See, tiny data, go to outcome. Let's add a vertical line to show where the mean is. We know from the favorite stats that the mean is 9. So we can just add the vertical line that crosses the x-axis at 9. See, this is the code. You go to histogram. I'm talking about that tiny data set, outcome 555. I'm talking about this one. Okay, this is small data set. I'm sorry, this one. Yeah, this small data set. Okay, tiny data. Then we call that data. That variable is outcome. We drew the histogram for tiny data, and then we put that one into. We got the variable. Variable has a value 5, 5, 5, 10, and 20, and then we put that into a data frame called the tiny data, and then we drew the histogram, and then it's been linked with the vertical line V. GF, vertical line, go to x-intercept, put 9, and color, put blue. See, that will give you this one. See, on the other hand, this one, this 9, rather than put 9, can you recall that one in the different way? The 9 would be my mean. See, I'm talking about, yeah, that's the same thing here. Okay, see, GV histogram, outcome, tiny data, GV and line. See, they don't put the 9. See. They put mean, see, tilde mean. Why? Because Here you don't have to say that data set again. You don't have to say tiny data $ mean. They know that you are already inside the tiny data because it's already linked. Don't put over here. You don't have to put tiny data $. See, you don't have to. You just say that draw the vertical line at the x-intercept at the mean of that particular data set. See, it will do that one. If you, instead of that one, if you put the median, they're going to do that one at the median. See, vertical line. See, this one, see, that's another way of doing that one. See, something else we're going to add. Now we can see, you can string these commands together using, I'm sorry, this one, see, V line, see. You can see this command, tiny data, x-intercept median, then the green, blue color, see, the mean and median, see, the other one is median. Instead of mean, you can put both median, you can add too, see, median, tilde median. You don't have to say tiny data, $ median. You don't have to say tiny data, $ mean. X-intercept should be drawn and give the different color, green color for median, see, 5, this is 9, you can remember, see. You can remember, see. Now you see it is pretty easy to answer how the median is the middle of a distribution, but in what sense is the mean is the middle? One way to think of the mean is as the balancing point of the distribution, the point at which the things above is equal the things below it. But what does it balance? Where are the things that are equal to both sides of the mean? See. So what we're gonna do, see, if you put this ones to balance, see, can you remember this is the median would be, see, green color, 5. See, because of this one, this data, so many data, these 3 data can be balanced with 2 data points. See? 2 data points. That's the middle of that distribution. Middle of the distribution is the median. But this is the middle of the location. See? You might think that the value below the mean balance with the value above the mean. Let's try that. Does 5 plus 5 plus 5, 10 and 20? No. See? If you go to see 3 5s and then 10 and 20, no. 50 does not equal to 30. See? This side 15, you get 3. You get 2 numbers. See? See, you might think that the value below the mean balance with the value above the mean. See, below the mean, you have how many numbers? See, 5, how many times? 5 times 3, 3, 5, 5, 5. See, 5, 5, 5, 3 of them. That's what they say. Below the average, there are 3 numbers. Each number has a value 5, 5, 5, 15. Above the average, you have a 10, 15, and 20. See, 10, 15, and 20. See, they're not going to be the same. See, 15 does not equal to 30. A bunch of smaller values. See, what we find below the mean is not going to balance a bunch of larger values. See, those are the mean. So what does the mean balance? Here it helps to think about the each score's deviation. What it balances. Look at the median. If you get the median, see, at the median, you have a 15 here. Again, see? And below that one, and then above that one, how many numbers? See? 10 and 20, see? 10 and, not the values. I'm going to say how many, okay? Not the values. As I say, the location. See? Location-wise, there are 2 above the median, and there are 3 above the median, see? And one value, see, one value is similar to this one, then there are another 2 on top of this one. See, these 2 will balance these 2. See, these 2 balanced by these 2. See, extra one. This has to be there because it is at that point. If it is at the median, this 1 5 has to be there. The other 2 5s, I'm going to go by the count. 2 other 2 values are same as the other 2 values above the median. See, below the median or on the median, you have 2 values. This one we don't count because it is on that one. Okay, the extra ones, I'm talking about the extra ones. In addition to 1, there are extra 2 data points. It's going to be on that one or below that. Is same as the number above the median. So median will balance this one for sure, not the mean. So what it would balance then? That's why they say that if we are talking about the mean would balance what? See, here it helps to think about each score's deviation, which is the distance above or below the mean. See, look at, you have 9 here. You have, can you remember, this is the first point, second one, third one. There's another one at 10, there's another one at 11. Okay, this one, see, take the gap, take the gap, take the gap with respect to the mean. 4, 4, 4, minus 4, minus 4, minus 4. How much? Below the average, minus 12. On top, the deviation, how far that point is away from the mean. 1 unit, 11 unit, put together, 12. That will balance the deviation. Mean not gonna balance the data value. Mean gonna balance the deviations. See? Or the errors. See? Errors. See? Look at this side you have a negative. This side you have what? Positive, sorry, negative 12. This side you have positive 12. If you add all these residual, these are called the residuals or errors. Residual, errors, deviation, same name. There are some who cancel off. So that means mean balances what? The deviations. Mean does not balance the data values. You saw that one. Mean does not balance the data value. See? If you think of that, this kind of balance that the 10 and 20, which is that 30, value-wise. Okay, I'm talking about value-wise. 30. On this side, you have 15. 1, 2, 5, 3, 5, 15. They don't balance. The median wise, yes, number, not the values. Median means number. How many above and below of that guy? There are 2 data points above, 2 data points below or on top of that one. That's a different thing. But mean balances the deviations. That's the mean is playing a heavy role here. In any given data set in this universe, the deviation with respect to the mean, deviation from the mean of that particular data set is, if you add all the sum of all these residuals or deviation, that would add to 0. See, any data set. No number other than the mean, not 8, not 8.5, not 9, will perfectly balance the deviation above the mean with those below the mean. Whereas the magnitude of score, especially an outlier, won't necessarily affect the median. It will affect the mean because the larger the deviation from an outlier has to be balanced with the deviation from the other data point. Every value gets taken into account when calculating the mean. Yeah. See? See? Look at that. So that's the very reason they're going to consider the mean as a good point to see that built up the model. See? Keeping this one, and then you're going to count that how far that each point is away from that one. You put together, the deviation will cancel off. See, not the same number, but the same the value. The deviation value. There are 3 deviations below the mean. There are 2 deviations above the mean. Number wise, there are 2 deviations. See, 2 deviations, but 3 deviations below the one. But value wise, see, above and below, they get cancelled off. So the mean balances deviations. Median balances the data values. Okay, that's what they will see. That's why they say here is the median, the middle of the distribution. There are an equal number of the data points above and below. Median balances the data number. See, the number of values, the median are equal to the number of values of median. That's median. The mean, this part, mean is balancing the point where the error above and below, or deviation above the mean and equal to the absolute deviation below the mean. So when you have the 2 different quantities, this single number, see, mean balances deviations or errors or residuals. We call that now. More specifically, we call the residual force when you have something in sample. We call error when you have something in population. Some deviation in, I'm sorry that, I think this is not connected. Yeah, okay. The mean, see, I'm gonna write this down. Mean is mean balances, see, mean balances deviations or errors or residuals. More specifically, we call the residual for the deviation of sample. We call errors deviation of the population data point. When they are deviated in the population setting, we call the errors. In the sample setting, when the data point deviated from the mean, okay? Deviation, balances, deviations from the mean, see? From the mean, okay? So the median does what? Median balances what? Median balances the given data points, data values. See, that's what they are to task. See, that's what they were having over. Why the mean is unbiased? Oh, that's a new word, unbiased. The errors in both directions from the mean are equal. The sum of the differences on the left of the mean is always the same as the as that on the right of the mean. The mean is not influenced by bigger values than by smaller values. Eh? Not more influenced by bigger values than by smaller values. Eh? Unbiased is not being unbiased means the error in both directions from the mean are equal. See, errors from this side and that side, if they are equal, we're gonna say unbiased. If they are biased, sometimes that the deviation coming from this one is more than that of this one. Okay? That is coming from this side. Okay? But it is unbiased means okay? The errors in both directions from the mean are equal. Okay? The sum of the differences on the left of the mean is always the same as that on the right of the mean. See, sum of the differences of the deviation is same as the that of the deviation of the right hand side, deviations on the right hand side. So that's why I call the unbiased. There's no biasness. I'm not talking about the number of data points. I'm not talking about that. It has to do nothing with the mean. You say that the deviations coming from this side, sum of the deviation is same as the sum of the deviation from this side. So anything above that one called positive. See, you know that 10 minus 9 is positive 1. 20 minus 9 is positive 11. 5 minus 9 is negative 4. 5 minus 9, negative 4. 5 minus 9, negative 4. See? Now we're going to go ahead and fit in the empty model. For the first time, we're going to fit into the empty model. That means we're going to get the data and then we are trying to fit in this one to see empty model. What that means, I'm not going to take into account other variable. I just say that's an empty model. Nothing has been explained. Nothing's going to thumb is by going by itself. Thumb been explained by its own mean only. See, its own mean only. See, that's why I call the null model. See, null empty model. That's what we are trying to learn here. For the first time, I'm going to use the word called the empty model. Empty model has another name, null model, N-U-L-L, null. Okay, the simple model we have started with using the mean to model the distribution of a quantitative variable. See, mean has been utilized to explain the quantitative variable. Mean, not another variable, not another variable. They are using their own mean to explain the build up the model. Okay, that's it. So understand what we are trying to do over here. I'm using its own mean. See, so I have a data. See, data. I have a data. I'm using its mean plus error. See, its own mean. See, data's mean. See. That's my model. In another way, I can say data has been modeled with the empty model. Empty or null model plus error. Other stuff or other stuff. See? It's the same thing. See? Its own mean. So there's another name for that one. Int model. See? Therefore, they write with the mathematically, they're going to write like this way: y equals y bar plus this letter, Greek letter, epsilon. See, this is y bar to indicate the mean. That's the mean of y. See, okay. I'm not going to use another variable to explain another one variable. I'm using its own mean to explain its variation, how it's going to vary, because we saw that above and below this mean, the deviation are the same. That would the mean is balanced. Mean is balanced in the deviation above and below that particular thing. That means when you're going to draw some kind of a data, all the data not going to fall onto the mean. It's maybe scattered over the places. See, so let's say that when you have that y over here on this side, let's say that y. For my convenience, I'm going to put the y here. So this y. See, this is y bar. That's the mean. That's the mean of y. See, that line somewhere. So if you have a data somewhere below, some data above, below. I'm not talking about the number. I'm talking about the deviation wise. They get cancelled off. See, you draw that. I'm talking about the dot plot. I'm talking about the scatter plot. There's nothing over here. See, there's nothing on this axis. In addition to that one, we can draw the histogram. You saw that we were talking about what are I'm talking about the y. For y, I'm going to use in a quantitative variable. Quant variable y. See? Y means a quantitative variable. In another way, quantitative data. Quant data, same thing. Or simply we call the data. See? Like that. That's why we're going to see these are the deviations. See, those are the deviations for each and every data point. It has been deviated from its mean. See, deviation. See, if you add the deviation above and below, they will cancel off. They will cancel off. See, they are using that one. That's if you use that kind of a model, the way that I have written over here, you are using empty null model plus the error occurred to say that your data, how far from that empty model, how far from y bar. So the difference between y and y bar is your error. Difference between y and y bar is your error. See, if you go ahead and tell this one error or residual is nothing but difference between the data point and y bar for each and every one. See, everywhere. See, you saw this one. This is my y. See, this is my y. I'm going to pick at one point. See, this is my y bar. See, for that particular point. See, so the gap is what? Y minus y bar. I do the same thing for the next one. The point is my y. Points are my y. In another way, point has another name. True data value, true value. And y bar has another name, estimated value. See? The difference is called the error or residual. True, see? Estimated value minus true value. And you put the absolute value to say that you are always looking for the positive, but it may be positive or negative. If it is below negative, sometimes estimated value is more than, look at in this case, estimated value is more. See, this is estimated value. See, more than the, see, this estimated value more than this one. Then if you take the difference, see, you get a positive. Or you can say my true value minus the other way around. If you want, you can write this way or this way. See, either this way or this way. True value minus the estimated value. Doesn't matter. Either way. If you do this one, first one, you get the negative, positive based on the way that how you're going to write it. But that's why we put the absolute value. So that's why they're going to, let's think about through the discounted student thumb length, and you go to tiny fingers, and then you look for these tiny fingers, and then whole data set is, and then you saw the 6 observation, and you draw the histogram for this particular data set. See? Modify this to save favorite statistic thumb length. You can remember favorite stats of tilde thumb data would be fingers. Oh, sorry, tiny fingers. This is a tiny fingers data. Tiny fingers. Tiny fingers. Go to histogram thumb data tiny fingers. Then GV line. See, you need the line what x intercept. Can you remember? Equals to period of mean x x int, I think x int, no. V line, okay, GV line we are missing. GV line, x intercept, okay, that's right. E line concatenated with the GV line. X intercept, that's right. It doesn't come. GV line, x intercept. If you want, you can put the color. It doesn't come. Gonna get from this side, it's easy. Okay. Okay. Let's get this one. Okay, thumb for tiny fingers. Thumb. Tiny fingers. Thumb from the tiny fingers. X intercept mean. Okay. What is this? Okay, sorry. Outcome tiny fingers. V line. What is the missing one? I'm missing something. Okay, we have to get this data. GV histogram. Okay, V line x-intercept at 9 instead of that one. Okay, we need the favorite statistics. Okay, that's why. Okay. Doesn't read that one. First, we have to get the favorite statistics. Okay. Outcome. Stats. Outcome.stats. Okay, I'm gonna go to that one and then get the fav stats of that variable. Okay, tilde data time any data histogram, then data tiny fingers, sometimes tiny fingers. Tiny fingers, V, this one, outcome state. From this one, I'm gonna take the mean. From this one, I'm gonna take the mean. Tiny fingers. Yeah, if you go ahead and then call this one outcome dot stats. That one too. See, so your mean is 62. Mean is 62.4. Yeah, 62. Sorry, 62. Somewhere here. See, mean is 62. Say then, if you go ahead and check that the deviations. See, deviations, you can see the deviation. They have drawn this one in on x-axis because it's a histogram. So see one value above that one. So this deviation, and there's another value, this deviation and this deviation. Those are all positive above one, and they will get cancelled off if you're going to add these three deviations. See? So how could you going to run the model? Now, for the first time, you're going to use something called the linear model, LM, thumb, tilde, who put the null model null and call the data. That will give you this coefficient. Coefficient means like what is for the intercept. What are you going to get for the intercept? What that means? Intercept means this same model. It is like a, see, it's like a straight line. See, that's the straight line. See, x-intercept. See, x-intercept. See, that's the x-intercept. See, that's the x-intercept. See, where it's going to go and cut the x-axis. That value is nothing but the 62. That value is nothing but what? The average of the thumb length. See, I use thumb y tilde. For the x, I don't put anything. I'm not talking about this graph. This graph, in order to draw the graph, histogram, you can remember all the time you put your variable on x-axis. X-axis to draw that. The way that I draw over here, see, you put the y. See, that's y. I didn't put this way y. I put this way to show you something to see this line this way. That's the same thing they have shown. See, horizontally, this way. In this, sorry, I showed you that horizontally here. They are showing over here vertically. See, that's the same thing. So like if you're going to rotate this one by 90 degrees clockwise, you get the pretty much the same thing. This is going to go to y-axis, and then you're going to see the same picture like this. See? See? This is actually y, okay? It's not a y, it's not on the y-axis. That's why I drew over here for you to get a clear idea. See, this is your thumb length. See, that's the thumb length. That's the thumb length. See? Y would be the thumb. It's called thumb length. It's the average. Average is how much? 60? 62, no? 62 average. Average is 62. And all the other points, you see, other data points. See? These 6, they were drawing this one for this 6, see? 56, 60, 61, 63, 64, 68. For the tiny fingers data, you have like a small data set. See, like that. See? You have a 56. So then you can say 56 below 62. This is 62. Y equals 62. See, the first one is 56. I'm talking about this one, 56. See, 56. Okay. If I'm gonna consider, see, this one like a 1 point and 60 again. See, somewhere here 60. See, and 61. See, 61 again. This one. So I'm going to, if I draw this one to separately on this one, you can see this. So what I'm saying, this is y. Y is thumb length. So I'm not going to have anything. I have my mean. Y bar is 62. My first point is 56. This is 56. The gap of this one is how much? 6. See? 6. And the other one is 60. Next individual, 60. The gap is 2. Then the other one is 61. Then the gap is 1, 61. See, then I have a 63. See, here 63, the gap is 1. Then I have a 64. The gap is 2. Then I have a 68. The gap is 6. See, above 6 get cancelled off, below 6. And 2 get cancelled off, 1 get cancelled out. The deviation, see, equally balanced. I'm talking about that, not the number. See, not the number. There are 3 in this situation. I'm not talking about the number. I'm talking about the value wise. 6 plus 2, 8 plus 1, 9. Above that 1 get cancelled out, below. See, that one. Then they say that the 62. If you use the linear model, LM, the coefficient, or the coefficient means like the way that we are writing over here. Here there are some, the way of writing this one down the road we can see. So there we're going to show the 62. See, if you want, you can add that one to, see, assign that one to another, a new variable. See, new object. New object. See, tiny empty model. Tiny empty model, and then you can print that one. That's another way of doing this. See, now we're gonna say that do the same thing for the full model. Okay, they say go to the empty model, modify this to fit the empty model to thumb. See, empty model. See, if you go to the empty, modify this to fit the empty model of thumb. If you go to the empty model, not the tiny empty model, this time we're gonna give a name to empty model, means LM, you put the y first, which is thumb, then tilde. I'm not drawing the histogram, okay? I'm going to put this is the model, how you write the model. Y first, thumb. This is what I'm talking about. See, I'm talking about this one. See, thumb equals to, see, thumb data, see, thumb variable, see. Variable. I'm fitting the variables, okay? Variables, okay? They are data, okay? Another way, this is the data. to what? Average of thumbs. That's my model. More specifically, that's my empty model. And plus, all the time, I have a deviations. Deviations means error or residuals. Deviations or error. See? That's why I write y equals y bar plus, if you want, you can say other stuff. Same thing. Okay. This any value I call y. This is y. This is also y. This is also y. 63 also y, the part of y. Y. See, y gonna change, but y bar fixed. Y bar only one value fixed. Y varies. That's why we call the variable. See? And you take the division for each and every data point, and then you got that one. So same way now this time, I'm gonna write the y first, then write the null, because I don't put anything for x. And give the data. This time for the data, they say go for the full data set fingers. This print. Now if you call that one, you can save the favorite statistic. Save stats. And we can say save stat again. Our thumb data would be your fingers this time. Fingers. Then make a histogram. Make a histogram of the thumb. See, you know how to do that one histogram. I'm gonna get this one to x-axis. See, look at the thumb this time. I'm gonna get to x now. See, I wrote after the tilde. Here, I wrote before tilde when it comes to the linear model, because it is fitting into this model. I'm not drawing the histogram for this model. It has to go, y has to go what? In front of what? See, that's the same thing I'm gonna write. See, y tilde. See, empty. You put the empty means that an empty. See, which is null. That's enough. See, y means what? Your data, thumb. You write like that. But when it's come to the histogram, since you're gonna have that x, you're gonna get your whatever the variable interested in, whatever the variable for which that you draw the histogram should go to the x-axis. Okay, that's the reason I put on x-axis. See, after the tilde, then you're gonna recall the data. Data. These fingers, and then chain with this one vertical line and go to the mean. See, tilde. Mean of the favorite statistics. Okay, now the data set would be favorite stats, see? Which is called thumb stat. Go to thumb stat and pick the mean. Or if you want, you can write this one in another way. Go and simply one shot, you can write here. I'm talking about this line. Okay, I'm talking about here. Instead of writing like that, see, you can do this one. So this way. Talking about that vertical line part here. See, you see this one is nothing but whose mean? Mean of thumb. And you can get rid of this one. Another way. The variable thumb. And this should be that chain with this one, otherwise you have to recall the data, okay? Otherwise that data, thumb stat data, it's coming from thumb stat, also consider like a data set. That's why I say go to that particular thumb stat data. Thumb stat means like a 5-number summary data and then pick the mean. That's the one way. But rather than that, you can say, let's say that, okay, I'm gonna get rid of this one. Okay, I'm gonna do with this one first and then if I cut off, That's 160. See, we have already run that empty model here. See, 60.1 for the full data set. For the then this one, then instead of that one, can we get that histogram with the vertical line by doing like this? Not found. Okay, sorry. We have to say fingers. Go to fingers and fingers down. Even though you call the fingers, it won't take it if you since you are because at this line you have to give the data set. Data means this data, okay? But the way that we did the other one, follow very carefully. This one. Look at this one. I'm picking mean from thumbstats. Within the thumbstat, that means from if you run this one, thumbstat means this one. See, thumbstat. If you run that one stat, v line, this one. Okay, I'm gonna run this one. Oh, what happened? Mean data thumbstat. Because this one is right. This is right. Thumbstat. I'm running that one. Okay, it works. Oh, look at the extra one. This one. That's the plot. Okay, now it will. See. So that one. See. From the thumbstat, go to this one like a data set and go to the what do you call the mean and pick that guy. That's what it say to draw that line. See, if you do like that, you have to put thumbstat. If you write like this way for the vertical line, x-intercept mean, see, you're gonna go inside the fingers data and that original data set and then find the thumb. It's mean, it's assigned to x-intercept, or you draw the vertical line at that point. See, it's the same. It's not okay. I'm gonna look at too many. Okay, and we get okay now. See, same. So see, that's how you're gonna do that. Okay, let's see this one. See. Then if you predict from this one, now what are you gonna do? You believe like that. What do you mean by the predicting? You believe you are all the data set as if it's not a predicting something for that next guy. Okay, this here prediction means different. Okay, now generating predictions from this prediction is different than if the same prediction that we were talking about earlier. Let's say that when we have a data set like a housekeepers, by looking at that the model, by looking at the shape, by looking at the 5 number summaries, sorry, the favorite statistics, by looking at those numbers, you can figure out, you can predict what would be the age of the next housekeeper. That's not what predicted here. This prediction is different in this linear model. We're gonna say as if this model is not, if the data is as if coming from the same place, see, the average, see, that's why this say over here very clearly. We just made a point that the mean of the sample distribution is the best unbiased estimate of the mean of the population. We use the mean as our model for the population, and if you want to predict what the next randomly sample observation might be without any other information, we would use the mean. In data analysis, we also use the word predict in another sense. For another purpose, using our tiny data set, we found mean thumb length is 62. So if we were predicting what the 7th observation might be, we got with the 62 mean. But if you take the mean and look backwards at the data we have already collected, we could also generate a predicted thumb length for each and every data point. See, you are talking about the 7th one. You are talking about you have a data 6 data points, You know the value of 6 data points. See, 56, 60, 61, 63, 64, 68. If the data go like this, you can draw a histogram for that guy, that small data set, by looking at the shape, plus by calling the favorite statistics of this guy, by taking the average. You can, because average would be the single number that we're going to utilize in order to do the prediction, and they say your next number would be on average 62. That's a one prediction. There's another prediction. Excuse me. That prediction is each value, I believe, supposed to be coming from 62, not the next one, the current one. 56 should have come from 62. It is not 56. See, that's the prediction for 56. See, that's a projection. See, 56 is 62, 60 is 62, 61 is 62, 63 also 62, 64 also 62, 68 also 62. That's another kind of a prediction. That's why they say first number, second number, third number, fourth number, fifth number. See, they all. But if you take the mean and look at, say predicted thumb length point already. This prediction answer the question: what would be our model have predicted this thumb length to be if we hadn't collected data? See. If we hadn't collected data, what would be these numbers? See? Our model have predicted these thumb lengths. See? What would our model have predicted these thumb lengths to be if we hadn't collected data? If we hadn't collected data, what would this model would assign for these even numbers? What? See, what are the numbers that the model have predicted for these thumb lengths? 62. That's another kind of a prediction. How do you get that one? See, by using this function, predict tiny empty data. See, I call that, this is the name of the model, okay? The name of the model. You can remember when you run the model, you have assigned that one to, see, oh, I think something happened. Okay. Okay, see, sorry. Yeah. So see, when you run that one, it has been assigned to empty model. See, been assigned to empty model. We can remember we assigned to empty model. You go to the empty model and then run the prediction on that one. See, this is for the previous one. This is not the empty model. This is a tiny empty model because we are talking about that small data set, not the full data set. See, tiny empty data. We'll display this one. They say the prediction and save the predicted length for each 629. This one, the print the new content of tiny. Then you can get the model, modify this to save the prediction from the tiny empty model. See, you're gonna get the value from the predicted value and put it back into that your original data set, your data set. See, and create another column. Look at. You call the column new variable called predicted to assign your value, predicted value into. See, go to the tiny fingers. This is the name of the new variable. See, these are the predicted value. And then this print the tiny fingers. See? Look at, you have a new variable, new column being created within the same old one. See, this is the real data. See? This is the predicted value or estimated value. See, it's the estimated value. This is the real value. The gap is called the error. That's what they are trying to do over here. See, look at the print out the thumb length as predicted thumb length for each student. Which student actual scores were closest to the predicted one? Actual. This is called the actual value. The real value, true value. This is called the predicted value, estimated value. See, which one is a number student 3 and 4? See, number student 3, 63, 62. Above the average, below the average, very close. See, thinking about the error, as I said earlier, data means this time you're going to write the mean. See, data equals mean plus error, then error is nothing but data minus mean. How do you find that one? You go to the thumb length and you're going to subtract the predicted value. See, thumb length, go to the data set. Name of the data set is tiny finger. $sign thumb. Thumb means the thumb length minus same data set. Go to the new variable predicted and find the gap. That gap gives you that error for each and every case. See, instead of that one, you can get the residual. These are the residual in another way. They say that modify this to save the residual from the tiny data set. See, you can see residual. They can call the residual. They can call the residual for that one. See, modify the file, save these residual in a new variable called. I'm gonna call this one a residual. See, and put it back into that data set, and then you're gonna run that one. See, this is the thumb length actual one minus the predicted one will give you residual. Residual will be put it back into the data set. See, look at that. See, real value, predicted value. This predicted value means you're not going to predict the seventh one. You are predicting that you, as if that your data not collected, what would that your thumb length for the first student? 62. That's the prediction here. In that sense, there's another sense that you can think about that if a new student going to be added to this one, his thumb length would be how much? 62 as well too. That's a different thing. Okay. In this sense, otherwise you might gonna think, okay, this 56 outcome becomes 62. 56 is the sum you got from the sample, but in a real population, it should have been 62. See? Now you can do the residual in another way using this function. See, you don't have to do in this hard way over here, in the long way. See, we did the long way. We did the long way. See, gap, different gap. Right? You can go and run the residual for the empty model, and you can get that one. So that's why they say modify this to save the residual from the tiny model. Calculate the term the easy way. What is the easy way? Easy way is this one. See? Okay. Another way of doing that one. And then create another variable called the easy residual and run. It's not called, they call the give a new name. See? Look at easy residual. Now they say that you calculated earlier the residual as well. They should be added to this one too. See, tiny fingers. See, modify this to. Yeah. Okay, I have to run that one first. This one, get this one first. Okay, get that one. See, and get that one first too. Okay, I'm gonna go ahead and run this one residual too, and then put this one too. See, I run, I call the residual, this call this one. See, you can get both ways, easy method and long way. See, you calculate the residual this way, easy method by giving the function resid, or finding the difference between the predicted value and real value would also give the residual. See, so this is called the, so see, this way, easy way, hard way, or whatever, you just simply call the residual, but they both would give you the same thing. They're gonna put it back, but in order to do that one, you have to make sure you run that one. See, then if you plot that one, you can easily say, see, this is the predicted value. See, 62. These are the thumb value. These are the residual. Look at this shape. If you draw the histogram for this real value and the residual, they look the same. This is for the predicted value. It's going to be one line, 62 only. But this is the key part. Your thumb length and this one. Okay. After this page, we can stop here. The rest I can just make a that. I think. Let me see how much we have. Yeah, that's okay. That I can make another video, but little bit that I explain this one, and we can stop here. Okay. So that means, as I mentioned over here, data means Data means data equals to mean plus error. So that one. Mean data means y. Mean means y bar plus error. Error, if you want, you can put the epsilon or something. So the error is nothing but all the time y minus y bar. See, y minus y bar. Error or residual. Okay. In a sample setting, we call the residual. In a sample, okay. Error we call the error in population. Doesn't matter. See, y minus y bar. Your data point minus y bar. See. So my key part is if you draw the histogram for y, okay, this is y histogram. If it is look like something, see, and then it's gonna be that in that case that let's say that 62 or something. I want to check that one. 60, I think 61 point something average predicted value. Okay, the residual. For the tiny data, this is for the tiny data. Okay, yeah, tiny fingers 62. 62. Tiny fingers 62. Okay, 62. Okay, and that's for y. That's for the thumb. They say that one, and then if you look at the histogram for error, see error. I'm gonna put this one error. They look the same. Only difference this one, this time it's been symmetric about 0. You have to notice that one. See, 0, error 0. It has to be because that you're gonna balance what? Error has to be balanced. See, that's what you can see here. See, you can draw the histogram for residual. See, look at it, it balances. Even over here, if you draw the 62, it balances. See, that means that with respect to this one, that's the predicted value as well. See, here 0. See, that's the key part. The shape wise, they both the same. See, so see, okay, then see this one. See, now note that the variable residual and easy residual are identical. This makes sense. Okay, you just use different method to get the residual. Here we plotted histogram of 3 variables: thumb, predicted, and residual. Thumb look like this one, predicted look like this one, residual look like this one. Residual and this should look the same all the time. Only difference, this one has the average at the center. Okay, this one average you can put, but here this 0 for sure. See, examine the distributions above. What does the distribution thumb data look like? See, what about the distribution of predicted model? Finally, what about the residual error? See, residual low error distribution of this one. Distribution of error. See, look at. See, look at this distribution. See, distribution shape. If you go ahead and shape, see, you can see that one. How they're gonna happen for the tiny data set. See, every number has, see, 56, 60, 61, 63, 64, 68. Those number has occurred one time. Same way the error. See, error has been, see, how much the error, that kind of a error, that error 6. How many of 6? Minus 6 and plus 6. See, you have a minus 6 on this side, plus 6 on that side. 1, 1. See, look at the height. Same. Look at the height. 1. It has occurred 1. But this time that on below that, see, negative 6 and positive 6, 1, 1. Negative 2 and positive 2, 1, 1. See, equally distributed about this point. Negative 1 and 1. Look at the height. See, 62 has happened how many times? See, 6 times. 60 times. 62 has happened 6 times. 1, 2, 3, 4, 5, 6. See? That's the frequency. You know, when you draw the histogram, on y-axis you have a histogram of frequency, and this side you can have that variable. This is the variable. Here, this is the variable. How many times the plus 6 has occurred? 1 time. How many times the minus 6 has occurred? 1 time. How many times minus the 1 has occurred? 1 time. Plus 1, 1 time, like that. See? Minus 2 how many times? 2 one time. My plus 1 how many times? Here, that individual numbers has occurred individually how many times? 1. Each one, 56 one time, 61 times, 61. Right. What's the different about the distribution data and error? As I say, see, the here it's been centered 0, see, 0. Here you have the 61. Can I remember 62 if you draw over here? Now they say the distribution of the data and the residual have the same shape, see, same shape, but the number on the x-axis differ across the two distributions. The distribution of thumb is centered at the mean 62, whereas the distribution residual is centered at 0. Data that are smaller than the mean, such as the thumb length 58, have a negative residual, but data that are larger than mean 73 have a positive. We know that. See? Positive residual level. See? Print out the favorite statistics of thumb and the residual tiny fingers for, see, this one, see, favorite statistic. Get the favorite statistics residual. If you decide to save them, make sure that to print them out, see. You know how to run that one, see. You see, get the favorite statistics for thumb. Get the favorite statistics for residuals. See? And if you decide to save them, make sure that to print them out, okay? So thumb length, you can remember that how to get that one. Fail that fail stats. You go to thumb, okay, tilde, thumb, comma, data equals tiny fingers. Tiny fingers. I think they were looking for the tiny fingers. Get the favorite statistics for the residual. How do you get that one? Okay, see. Fail stats of, what's the name of that one? They call the variable. Variable is the tilde. Residual. Yes, we call that one residual. Okay, residual. And what's the data? Data. Residual coming from etc within the residual, the tiny data fingers. Thumb fail stats. Thumb. Oh, percent. Okay. First one and the second one. First one for that thumbs. Second one for the residual. See, residual. See this one. You look at this one. See, E stand for 10 to the power. Okay, 10 to the power negative 16. E stand for 10 to the power of negative 16. That means almost 0. See, almost 0. 0. Okay, that's the same thing that we see. It's very 0. Okay, and then see, minimum value. See, here. See, this top one for this one. Okay, 56 minus 6, Q1 and all this stuff. Especially the mean. See, here mean is 2. Here mean is this one. Minus 2.959872 times 10 to the power of negative 16. E stand for 10. Okay. And when you're going to write that one in scientific, with the scientific notation. See, number of items 6 and no missing data. See, that's why this. And the same way that, see, then you can add, see, you can just, see, you get the empty model, then you can play with the same thing with the fingers rather than tiny fingers for the whole data set. You can pretty much the same thing, see, and then you can have like a full scale, not like this kind of a histogram, very full histogram, see, and then this one, predicted one. And if you go to the residual and this one look the same, only difference, this will be centered around its mean, which is 61 point something. This one will be centered around definitely 0. always zero, residual. That means that average of residual is always zero, because of that average of the data set balances the residual. Okay. So what I'm gonna do, I'm gonna do another video and upload tomorrow that starting from here and with the more detail, and then I'm gonna stop over here, and then I can pretty much this one done this chapter. I think only thing that you have to run with the linear model, that function, predicted value, those kind of basic stuff. Okay. So if you don't have any question, that I'm gonna let you go, and then I'm gonna wind up over here. Then see you guys either on Wednesday at the help session or on Thursday. And you guys have a good night and stay safe and be well. Okay. If you have any questions, we can discuss. If not, I'm gonna wind up over here. Okay. Take care. Have a good night. Okay. Take care. Bye. Good night. Thank you.